Hello everyone, I am Kumaran, your physics faculty at Aakash, and how is everyone doing? I hope everyone is having a great time, and we would be continuing our discussion with the same AIATS plus phase 2, the test which was conducted on your Republic Day. Okay, and we will take our discussion forward from where we finished last time. If you remember, we were discussing work, energy and power, right? Constant force, variable force. So from that, we are going to continue our discussion today. All right, so let's begin. These are the topics we would be discussing one by one in serial wise, right? So let's begin with work, energy and power, right? So if you remember, last time we were talking about work, right? And just a minute. We were talking about work. We had discussed two formulae, right? Which is the original formula, which is force vector dot displacement vector. And if you wish to revise it again, you can go back to our previous session, which was conducted last week. I remember slot number 2, right? So this formula is a classic formula, you can use it. So for, let's say, constant force, right? Constant force is being applied on an object and the object is being displaced by d vector or displacement vector. Another formula we had written, f vector dot dx vector, right? And then I had put this integration sign. If you remember, why did we do this? Because at each point of the displacement, the force vector is changing, which means it is a variable force, right? And here we have to integrate, right? We have to do integration. And lastly, we had also written another formula for work done. It is equals change in kinetic energy of the body on which work is being done, right? So change in kinetic energy, which means final minus initial, right? So K final minus K initial. All right. Now before we move to the question, let me also discuss some small examples for integration, right? Which would be useful for your next question. Small mathematical formulae. Let's say integral x bar n dx, right? So what would it become? It becomes x bar n plus 1 upon n plus 1, right? Plus a constant. So plus a constant. But here the integration we are doing is, remember that we would be putting limits from this x to that x. So that constant won't be coming, right? So let me give you an example. So let's say integral dx, right? So what would the answer be for integral dx? Here if you see, here if you compare, what can we say? Here it is x bar 0 dx. So x bar 0 means answer would be x bar 0 plus 1 upon 0 plus 1. So answer will be x only. So here answer is x. And let's say take another question, x cube dx, right? So here answer is x. You can take another question, let's say x cube dx. And here simply the answer would be x bar 3 plus 1 by 3 plus 1. So x bar 4 upon 4 plus constant. And here also plus constant, right? So let's go to the question. So why are we doing all this, right? So if you see, this question had come in your previously conducted AIATS, that the work done by force, we have to find out. The force is given, and if you see here, this force, is it constant or variable? It's changing, isn't it? Yes, good morning, Janak. It is changing with the value of x, isn't it? You change the value of x, force will also change. And we have displacing the block from this x to that x. So here, that work done, which work done we would be using? F vector dot dx vector, right? And if you see this F vector, what is its direction? It is along I cap meaning, let's say along this direction, right? And we wrote F vector dot dx vector. What about dx vector? That is in which direction? We are again moving from, see here, 2 meter to 3 meter. We are also again moving along the x-axis. So dx vector is also along the x-axis, right? It is also in this direction. So that means f vector dot dx vector, what would it become? If you remember the dot product, right? We had written last time also, this becomes fd cos theta, right? If you want, I can write it over here, right? I will write over here, fd cos theta. So here if you see, they are both along the same direction, so cos 0 degrees, cos 0 is 1. So f dot dx becomes f dx only, right? So let's do the integration, f into dx. F into dx, this would give us the work done, right? So integration of small work done, right? So that's it, you have to do the integration only. So put in the values, that is 3x square plus 2 into dx, right? And remember, I said we can put the limits also. Here what are the limits? 2 meter to 3 meter, right? So x equal to 2 to x equal to 3. Now we can split this bracket and we will get 2 more integration terms. See, it becomes integral 3x square dx, right? That 3 you can take it as common outside this integration symbol, from 2 to 3, 3x square dx plus 2 dx, the 2 again will go out of the integration symbol, so 2 dx. This also from 2 to 3. Right? Now use the integration formula that we did just now. What is integral dx? It becomes, check here, x only, right? And what about this one? Integral x square dx, it will become x power 3 by 3. So 3 into x power 3 by 3, and we have to put the limits also. So limits we are putting from 2 to 3 plus 2 times x. Right? So x, we're putting the limits from 2 to 3. So that's it. Now you have to solve it. Simple calculation, right? So 3 and 3 will get cancelled. Put the limits now. It becomes 3 cube minus 2 cube, right? So 3 cube minus 2 cube plus 2 times, put the limits again, 3 minus 2, right? So 2 times 3 minus 2. So this is how much? 27 minus 8, 19. Plus that is 1, so 2 into 1, 2, so 19 plus 2, 21 joule, it's 21 joule. So see, small integration was done here. If you know that integration formula, you can do this. Not much complicated question this was. Very well. Now see this question. Let's do a similar question, okay. See here, again we are being asked to find the work done, but here see, no x component has been given, or y component is also not given. In terms of t it is written, right? In displacing a block of mass 1 kg starting from rest, it is given starting from rest. That means initially velocity was how much? So initial velocity was 0, right? Then mass is given, mass, let's say we are taking it as m, force is given, and see in first 5 seconds. So total time upon m, and mass is given how much? 1 kg, f upon 1, so acceleration would be 4t I cap, and you have to write the unit also. So unit would become meter per second square, right? Meter per second square. But for now, I am only writing a is equal to 4t. You already know what the limit is, right? So a is equal to 4t. Now, can we express acceleration in terms of something? Acceleration can also be written as dv by dt, right? So dv by dt, this equals your 4t. Take this dt over there. So dv is equal to 4t dt, then integrate it both sides, right? So dv is equal to 4t dt. Okay, and we will do integration. When you do integration, that 4 is a constant, it will come outside, right? So I'm directly writing the symbol over here. And again, if you see at t equal to 0, what was the velocity? 0, right? So t equal to 0, velocity is also 0. Then at some time t, we want to know what the velocity is. So let's say I'm writing it as t, and we want to know what the velocity is. So integral dv is what? Velocity v only. So v this answer would be V, and limits are from 0 to V. So when you put the limits, what would it become? V minus 0, right? And integral t dt, it was, see, integral x dx, it was x square by 2, right? So here t square by 2, t square by 2, and that 4 and 2 will get cancelled, right? And then you put the limits again. So this becomes 4 multiplied by t square by 2, right? So t square by 2. It is t square by 2 minus 0 square by 2. That term is gone. So t square by 2. So what does V become in fact? So velocity is nothing but 2t square, right? Velocity is nothing but 2t square. And if you want, here you could have directly put t equal to 5 seconds. Then you would have directly found the velocity also, which is what we are going to put over here. So put t equal to 5, put t equal to 5, you will get the final velocity, right? So final velocity is how much? 2 into 5 square, 25 into 2, 50, 50 meter per second, okay? And we are being asked to find the work done in first 5 seconds. First 5 seconds. So work done, you can directly write the answer. Change in kinetic energy. So K final minus K initial. K final minus K initial. And if you see, V initial is 0. So K final, K initial, it would become what? It would also be 0, right? K initial is also 0. This is 0. So K final only we wish to know. And K is kinetic energy. What's the formula for that one? Half mv square. So half, mass is how much? 1 into V square. V is how much? 50. So 50 square, right? So 2500 by 2. What's the answer? 1250 joule. 1250 joule. There is also another method of doing the same question. If you wish, you can try, right? There are plenty ways of doing the same question, okay? So if you see here, first I found acceleration, then I found velocity, right? So we ended up at V is equal to 2t square. So another way of doing the same question, right? So V is equal to 2t square. This V you can express in terms of displacement also, right? So V you can write it as dx by dt, isn't it? So dx by dt is equal to 2t square. That means dx becomes how much? 2t square dt. And work done, what is the formula? Work done is integral of f dx. F was how much? 4t. So put over here, in place of f, write 4t. 4t. Dx was how much? This term. So put over here 2t square dt. And here what's the limits we have to put over here? The limits we will put time as the limits, right? So time initially was 0, and finally in the first 5 seconds we are supposed to find. So if you solve it, you'll get the same answer. If you want, you can check, right? If you want, you can check. The answer will come to be the same. 1250 joule. Okay. Let's see another question. Again from work done. See here, F vector is given. But if you see in the previous 2 questions, that force was variable. So one force was varying with position, one force was varying with time. But this force, it's not varying, it's constant, right? See here, there is no x or t terms, it is a constant force, right? And displaced from one position to another position is given, isn't it? So this position, I am taking it as r1 vector. Remember, position, we have to take it as r vector, right? So r1 vector to r2 vector, right? So one position to another position. How will we find the displacement? Displacement would be final minus initial, right? So displacement d would be nothing but final minus initial, right? You just have to subtract them. Just subtract. See here, 2 I cap minus I cap, it becomes I cap only. Then minus 3 j cap minus 2 j cap, it becomes minus 5 j cap, right? So minus 5 j cap. And what will be the unit? It is in meter, right? Force vector is also given, so you have to find work done. Use the direct formula, F vector dot d vector. right? So F vector is how much? 3 I cap dot D vector is how much? I cap minus 5 j cap, right? So you just have to do simple multiplication, right? So see here, if you see, right? So what would be the answer? Can you tell me? What would be the answer? See, 3 multiplied by 1 is 3, right? And 4 multiplied by minus 5, it is minus 20. So the answer would be minus 17 joule, right? Minus 17 joule, right? Now you could ask the question, well, why did I do like this? Why am I not multiplying 3 I cap with minus 5 j cap? Well, look, it will become 0, right? It will become 0. Why? Because I cap dot j cap, it would become how much? See here, I cap dot j cap. They are both unit vectors. The angle between them is 90 degree, right? X axis and Y axis. So modulus of both vectors, mod of I cap into mod of j cap into cos of angle between them 90 degree. So that becomes, it means 0, right? So I cap dot j cap is 0, j cap dot I cap is also 0. So that is why we only have to do these terms, I cap with I cap, j cap with j cap. Okay, anyway, so this we are done. Good afternoon, good afternoon. Good afternoon, Subhash. I hope you are having a good day. All right, very well. So let's continue. Under collisions, I will just give you a brief theory. Based on that, we will do the question, right? So in collisions, always you have to remember that the total momentum, right? Total momentum remains conserved, right? So let's say we are talking about collisions in 1D, a simple collision, right? Straight line, 2 blocks are moving and they are colliding, or 2 balls are moving, they are colliding. So total momentum will remain conserved, okay? And also remember that the kinetic energy changes during collision. During the deformation is happening, then kinetic energy will change during the deformation, right? So here I am primarily talking about 2 collisions only, right? So the first collision is your perfectly elastic collision, right? And the second one, perfectly inelastic collision. Perfectly inelastic collision, right? So what does this mean exactly? And what does that mean? See here, so what this means is, so let's say for example, 2 balls, they are approaching each other, they are colliding. So what will happen during collision? Deformation will happen, right? Deformation will happen, and you need to remember, so what happens after the deformation, right? So you can write down both masses, right? They move together. After the collision, right? Which means, let's say initially both of them were having some kinetic energy, but the moment they collided, right? The moment they collided, what happens? They start moving together, right? Which means after collision, they are not separating. They are starting to move together, which means there has been some deformation, right? There has been some deformation. If I have to explain, see here, they're colliding like this, and some deformation happens, like some interlocking or some deformation happens, so they stick together to each other, right? So they move together, right? And we will say there will be loss of kinetic energy before and after, if you see, right? So there will be, you can say, maximum loss in total kinetic energy before the collision, right? Total initial kinetic energy, right? And there is also another symbol which we use, as you will see in the next question, which is E. E stands for coefficient of restitution, right? So this coefficient of restitution, its formula goes by relative velocity of separation divided by relative velocity of approach, right? So but as I said, they are moving together, so they are not separating. They are not separating. So what will be relative velocity of separation? 0. So what will E become? E is also 0. Relative velocity of separation becomes 0, so that's why E is also 0, right? What about here? Here there won't be loss. So we will say initial kinetic energy is equal to final kinetic energy, right? So I can write like this: initial kinetic energy equal to final kinetic energy. So there is no loss of kinetic energy, and obviously remember, momentum will remain conserved for both collisions, right? And what about E here? E will be equal to 1, which means they collided and there is no deformation after the collision, right? So that is why no kinetic energy is being lost. If here maximum deformation is happening, that is why maximum kinetic energy is being lost. All right. Now what about E? What are the values E can take? Right? E can take values between 0 and 1, and it can also take E equal to 0 and E equal to 1 also, right? So let's see what the next question entails. See here, coefficient of restitution for a perfectly elastic collision. Just now we studied, right? For perfectly elastic, E is equal to how much? 1. This will be the answer. For this one, E would be equal to 0. That implies it is perfectly inelastic. Okay. Very well. Now see this question. Two balls of mass m are moving towards each other with same speed v, same mass and same speed. Like this they are moving, and collision is happening. It is perfectly elastic collision. Then the loss in kinetic energy due to the collision they are asking. Just now we studied, right? If it is perfectly elastic, there will be no loss of kinetic energy. No loss at all. Okay. So that means, what is the answer? Straight away you have to tick 0. Right? Straight away. And remember, E is equal to 1. Just some additional information. And no loss of kinetic energy, right? And please don't get confused with what I have written over here, right? It means this would be there during the collision, which means during deformation is happening, right? So initially and finally, what are the changes in kinetic energy that I have written over here? All right, very well. Moving on to nuclei, right? This we discussed in detail, if you remember, in last chapter, right? Yes, Mukesh Kumar Mishra, good afternoon, good afternoon. All right, very well, see here. We discussed in detail last time how the radius of nuclide varies with mass number, right? And mass number, if you see, they are asking here, see, the number of nucleons they are asking in germanium. So that number of nucleons is what we call as mass number, right? And the radius of germanium nuclide, let's say radius, we are calling it as R. Germanium's radius is twice of the radius of beryllium, right? So I can write, let's say R1 2 times of R2. R2 is radius of beryllium nuclide, right? So, and we are also studied in last time, right, that R is proportional to A to the power 1 by 3, isn't it? Or we can say, if you cube both sides, R cube is proportional to A, right? So what will be the ratio of the radii if I take over here R1 by R2? It will be how much? 2. So cube both sides, cube both sides. So what will happen if you cube? See, 2 cube. And R1 by R2 whole cube, what can you write it as? It is proportional to A, right? A is your mass number. So this becomes A1 by A2, isn't it? So I hope everyone is able to follow. It's literally almost the same question what we did last time. Literally the same. Just a few modifications have been made over here, right? So this becomes A1 by A2. 2 cube is how much? 8. A1 is for R1, right? R1 is for germanium we have taken. So A1 is for germanium only. That's what we have to find out. A2 is for beryllium, right? And if you see in beryllium, what are these things? right? This 9 is what we call as mass number, the figure that is written at the top, right? So this is your mass number, 9. What is this 4? 4 is what we call as atomic number, which means the number of protons. So we would say Z is equal to 4. Anyway, so mass number is 9. So put 9 over here. A1 will become how much? A1 will become 8 into 9, right? 8 into 9 equals 72, right? And that was your answer over here. That was your answer. Okay. And let's say if I had asked additional question over here, which is, we know the ratio of the radii. So let's say I'm asking ratio of the volume, right? Then what would you do? Then what can you do? So see over here. This also we did last time, right? Volume ratio is nothing but the ratio of their mass number. So it is simply A1 by A2. A1 by A2. And A1 also we have found, right? A1 was how much? 72. A1, A2 itself we have found. So 8. So ratio of volume is 8:1, right? And similarly, ratio of densities also they can ask. So what would that be equal to? 1:1, right? 1:1, right? So this was literally the same topic. All right, everywhere. Anyway. All right, so that one was from your 12th class, right? So now we are moving on to next topic, which is gravitation from your 11th class. See over here, last time we did not discuss about acceleration due to gravity, right? We had only talked about Kepler's laws, if you remember. In Kepler's second law, we were especially talking about that day, right? So let's say this is your Earth, right? Earth, right? And Earth has, let's say, center over here, right? And let's say I'm standing on the Earth. Obviously, I'm standing, right? So let's say I'm standing over here, right? Standing on the surface of the Earth. And since I'm not inside the Earth, or let's say I'm not gone into the Earth at a depth, I'm not standing at a depth, only standing at the surface. So what can we do? We can assume this whole Earth to be concentrated at its center, right? So which means we can assume this whole Earth to be over here at this point, right? And this is me, right? This is the person. So all Earth is over here. So mass of the Earth, remember, is me, and let's say radius of Earth is re, right? So what will be the force of gravitation that the Earth will exert on me? That will be equal to what? How much? G, right? Remember, G m1 m2 by r square. So mass of Earth is me. My mass is m upon r square. R is the separation between me and the center of Earth. So how much distance I am from the center? R only. So this becomes r square, isn't it? And we are wanting to find expression for G. G is your acceleration due to gravity, right? So this F I can also express as equal to mg. This we have studied in your lower classes also, right? So from the here, what's the expression you are getting for small g? You are getting, see, m and m will get cancelled. G me by re square, G me by re square, right? So this expression connects small g with mass and radius of the planet. And remember this g, where are we finding it? Are we finding it at a depth, or are we finding it at a height from the surface, or at the surface? This is exactly, has been found exactly at the surface, okay? Remember, this is at the surface only we are talking about, huh? All right, now can we find another expression, let's say in terms of density? So what we have to do, we have to convert this mass in terms of density, right? So density, remember, is mass upon volume. So mass is how much? Mass is me, radius is re. So density is mass of Earth upon volume. Volume is how much? 4 by 3 pi r cube, isn't it? Volume is 4 by 3 pi r cube. So in terms of, instead of me, you can just substitute them. So what it becomes, see here, I will write here 4 by 3 pi r cube or re cube into rho, right? Whole divided by If you do this, you will get a new expression for small g at the surface. So see here, RE square will get cancelled, isn't it? See, these terms get cancelled. So what remains? It remains 4 by 3 pi g rho and RE. This is what remains, right? So two expressions we have found for gravitation, acceleration due to gravity at the surface of Earth, right? So let's see what the question is asking here, right? So they have said two planets have the same average mass density, that means they're talking about rho. So rho for both planets is same. The radii in the ratio 2:3, that means radii ratio, right? So R1 by R2 is given as 2:3. Ratio of their acceleration due to gravity they are asking. So G1 by G2 we are supposed to find. So which formula of G we will use? Which formula? We will use this formula or this formula? See? We will use this formula. Obviously we have to use this formula, right? Because G is connected to rho here, right? So G, we can say, is proportional to rho into R, isn't it? Rho into R. But remember, rho is constant over here. Rho is constant. So we can directly write G is proportional to R only. That's it. Right? So that means the ratio, right? So G1 by G2 becomes R1 by R2. R1 by R2 is 2 by 3. So the correct answer would become how much? Correct answer would become 2:3. Okay? Simple, straightforward. If you know the formula, it will be directly straightforward. You don't have to do any calculations, right? You can all do it in your mind itself. But you have to remember these small steps. All right, very well. And if you remember last time we talked about Kepler's law, Kepler's second law, right? We proved, and those of you who are, let's say, joining us for the very first time, you can please check the last session I had with you guys, right? Where I proved the gravitational force acting on a planet revolving around the sun in an elliptical orbit. That force is a central force, torque becomes 0, angular momentum becomes constant, and because of that, aerial velocity, we were getting something, isn't it? See, this was what we did last time, right? Kepler's second law, right? So aerial velocity, dA by dt, right? What did we write last time? We wrote it is equal to L by 2m. L is your angular moment, right? Angular moment of the planet, right? So angular momentum becomes constant. That is why this dA by dt is also constant. So this is equal to constant. We proved last time, and this is Kepler's second law. Okay, and this, what do we call this as? We call this aerial velocity, right? We call this aerial velocity. And also remember, just some additional information that I would like to give you, although it's not connected to your question, we will see on the next page, right? The time period, right? What can we write the time period as? See, let's say time period, can I use this expression? Area swept upon aerial velocity. Right? Area swept, right? So remember, this is an ellipse. An ellipse, this is the major axis of length 2a. This is the minor axis of total length 2b. So what will be the area swept? We call it as how much? Pi a b, right? This is some additional information, right? And aerial velocity, it is a constant. Aerial velocity magnitude will be how much? L by 2m. So I'm simply writing L by 2m over here. L by 2m, right? And remember, this will be a constant, isn't it? This area is a constant, this is also constant, time period is also constant. So time period of the satellite in completing one revolution, right? It will be constant only. All right. Now this is for ellipse, right? Remember, this we wrote for ellipse. Right? Now let's say what happens if this satellite is revolving in a circular orbit. Then what will be the formula for time period? So circular orbit. Then what will I say the time period as? See, time period, you can use the same formula over there also. The same, exact same formula, right? Area swept will be how much? For whole circle, area swept will be pi r square, right? From this point it is coming, doing one revolution and coming back to the same point. So area swept would be pi r square upon aerial velocity, that is L by 2m. And L, what was the formula? L is your mvr, isn't it? mvr. Why mvr? Because in a circular orbit, the velocity vector will be always perpendicular to radius vector, always perpendicular. But here that was not the case. So here we won't directly write mvr. We have to take the angle also, right? Velocity and radius vector, they are not perpendicular. You can check my previous explanation as well. So L by 2m, right? L by 2m. And if you see mm get cancelled, 2 goes up, r and r square get cancelled. So what remains? If you see 2 pi r, see 2 pi r upon v. And this is the classical formula which you must have been studying still from your 9th class, right? But from this formula also you are getting the same time period. So you can remember it like this as well. Alright, anyway, let's come to this one. This we did last time, like literally the same question. The law of constant aerial velocity of a satellite is an outcome of conservation of angular momentum, isn't it? This is constant, that is why aerial velocity is constant, right? Very well. So we're done with gravitation as well. So we are moving to the next topic, mechanical properties of solids, right? Mechanical properties of solids. Okay, aspirational boy is asking which book we have to purchase for physics. I would say the Aakash package, that is self-sufficient, right? If you do the NEET momentum booster packages, or if you solve the regular packages as well, there is a lot of coverage given to lots of questions, right? I think good practice would be there if you're able to solve all of them, right? And you have to keep solving from time to time, right? You can take some small breaks, you can switch subjects as well, but you have to keep solving. Practice makes a man perfect. Isn't that what they say? All right, anyway, let's come to mechanical properties of solids. Right? So here I want to discuss this curve, stress strain curve, right? So let's see. And we are drawing this curve for a metal. It's a general curve that is also given in your NCERT. Please study it. It is given for a general metal, right? So general curve. So see here, and this is your stress axis, and this is your strain axis, right? Strain axis. So let's say this is a rod I am having, right? This is a metal I am having. I am putting a force, right? I am pulling that rod in this way. So what will happen if I am pulling it, right, perpendicular to its cross-sectional area? What will happen? It will elongate, isn't it? In pulling it, it will elongate like this. So initially, as I increase the stress, the strain will increase, right? So it would be a straight line. It would be a straight line like this. All right. Or we can erase it. We can draw a shorter one. Right. Let me draw a shorter one, right? Let me draw again. This is your stress, and this is your strain. So initially, as I increase the stress, it would increase proportionally, right? Proportionally meaning that the stress would be proportional to strain, right? Initially. So it is increasing in a straight line, sort of, right? So let's say this point, I'm calling it as A, right? And then as I increase the stress, so the curve will go like this, okay? It goes like this. Let me label these points one by one. So this is your point A, this is B, C and this is D, right? This is D and this point, right, A. So from O to A we can say, right? So from O to A we would say it is increasing proportionally. So what that means is if I remove the stress, right, I am elongating the rod, if I remove it, remove the force, it will go back to its original dimension, right? So complete elasticity is there, right? So elastic behavior is observed, isn't it? And this region is where Hooke's law is valid. And what is Hooke's law? Hooke's law is this only, stress is proportional to strain. And if you remove the constant of proportionality, you will get a constant that is called your modulus of rigidity. So stress is equal to that modulus into strain, right? So I can write over here modulus of elasticity equal to, what will it be? It will simply be stress upon strain, okay? Stress upon strain. Now let's go to the next region, that is from A to B, right? Right? A to B, see what happens? Here also again, is it a straight line? It is not a straight line, isn't it? See here the curve, it's not remaining a straight line anymore, it is bending like this, which means, so here stress won't be proportional to strain, okay? So here if I write stress is proportional to strain, this we cannot write over here, okay? Here it won't be proportional, but remember here also this elasticity is observed. That means until B, right? So from O to B, if you remove stress at any point, that object or that metal will go back to its original dimension, right? So let's say if you are removing stress over here, it will come back to 0. 0 means strain is 0, so no elongation is there, okay? And this B, right, and this A, they have some special names also, right? So let's say the stress at A, you can call it as proportional limit, right? Right, proportional limit. And what about B? The stress at B, you can call it as yield limit, right? Yield limit. Okay. Now what happens after B then? Obviously, after B, that elasticity won't be there, because I just now said from O to B only that elasticity is observed, right? So from B to C, there won't be any elasticity, which means from B to C, let's say over this point, if I am removing the stress, the object won't go back to its original position, which means there will be some permanent deformation, right? So from B to C, there will be permanent deformation, right? And the C point, we call it again as breaking stress, right? Or we can also call it as maximum stress, right? And if you see for this whole material, C is the maximum stress that is being applied, right? If you see, if you draw dotted lines on this stress axis, this much is the stress. That is the maximum value which is being applied on that material. No more stress is applied above breaking stress, okay? And D is called what? D is called your fracture point. If you want, I can write it over here, right? I can write over here, D is called your fracture point, or you can also call it rupture point, right? Okay, rupture point. So remember what I said, from O to B only elasticity is observed. From O to B, after B there is plastic deformation. So plastic region, this would be called after B onwards. Before B it is elastic region, okay? So please remember everything that we discussed. Now let's see the next question, right? it says Hooke's law is valid up to. Hooke's law is valid up to, they are asking. Which one would be the answer? Pretty simple, right? Because just now I said Hooke's law is valid only up to A only, not until B. B is your yield limit, but only until proportional limit Hooke's law is being valid. So the correct answer would be, okay, obviously it won't be fracture point, right? Because once it crosses B, plastic deformation is going to happen. 100% it is going to happen. All right. And a few more points. Let's say you can, if you want, you can write it down. So let's say after from C to D, right? From C to D, let's say the C to D, they are far away. Okay, they are far away. What does that mean? What does that mean is that even after you remove the stress, that material is being elongated, right? It is elongating, which means, so if C to D is large or very large, we will say the material is ductile, right? This is just some extra information. And obviously if C to D is very, very small, very, very close to each other, that means after a few moments that material is fracturing. That means it is not ductile. That means it is very small, right? We call it brittle material. Okay? Brittle material. All right, very well. This we have done. Now see over here, Young's modulus can be measured in, they are asking. So the units they are asking, right? Young's modulus is written for solids only, and modulus of elasticity, what did we write the formula as? Stress upon strain, right? So stress upon strain. Stress is what? Force upon area, isn't it? And strain is change, relative change in the original dimension. So let's say it is delta L by L, right? Now what's the dimension of force? Dimension of force, see, these things you have to remember by heart, right? You are not supposed to find these things on the NEET exam. You have to remember it by heart. So dimension of force, it would be, or let's say here they are not asking dimension, they are asking unit only. So what will be the unit of force? Mass into acceleration, right? So it is kg meter per second square for force. And what about area? Area is your meter square unit. Now what about change in length by original length? Both are in meter, they will get cancelled. So this has no dimension or no unit. All right. So the unit of Young's modulus would be this only, right? So if you solve them, what will you get? kg meter inverse, second minus 2. This would be answer, right? kg, let me write it down. Okay, m minus 1, s minus 2. That's it. If you want, you can write their dimensions as well, right? So do you want me to write the dimension? Let's write it. kg's dimension would be m inverse meaning L inverse, second inverse meaning, okay? All right, so let's proceed. We have reached laws of motion, right? And in laws of motion, if you remember, we have discussed in detail Newton's second law, right? What does Newton's second law say? Net force is equal to mass into acceleration, right? So here if you see, we have a rocket, right? So let's say I'm drawing a rough diagram for a rocket, right? This is your rocket. It has a mass. Let's say the mass, I'm calling it as m. So the rocket's weight will be in downward direction, mg, right? And they are saying it is blasting upwards with an initial acceleration. The direction of acceleration is also given. It is moving up with acceleration, let's say a. This is acceleration a, right? A is value given, and the initial thrust of the blast they are asking. Now this thrust will be in what direction? Obviously it has to be in upward direction, right? Because the rocket has to move up, right? So let's say I am calling this thrust as Ft, F thrust, right? So now how will we be using Newton's second law over here? What was Newton's second law? That F net is equal to mass into acceleration, right? force is proportional to change in momentum. We had derived it. It becomes mass into acceleration. So what is the net force over here? Rocket is moving up. So net force would be Ft minus mg, right, equal to ma. And what would F thrust become? It becomes m into g plus a, right? You take it over there. So F thrust becomes m into g plus a. M is how much? 4.5 into 10 to the power 4 into g plus a. G is how much? 10 meter per second square. That's a standard value. You can take it always. And a is how much? 20. So g plus a becomes 10 plus 20. That is your 30. Right? 30. Now 4.5 into 3. That becomes 13.5. And the 10 goes over here, 10 power 4, and that becomes 10 power 5. And it is a force, so answer would be in Newton. You see over here, Newton, right? And please keep going through and keep revising. Okay, we will do some more interesting questions in our next session as well. All right, see here, see the next topic. I would also like to talk about these two frictions, which we did not do last time. We will discuss some small theory regarding them as well. Okay, see here. What is the objective of any friction? The objective of the frictional force is to stop slipping between two surfaces, right? So for example, let's say this is one surface and this is another surface, this body, right? This body is slipping on this surface, right? So the friction that is present over here, it will try to prevent this body from slipping, right? So that is the objective of static friction, right? And it is, we call it self-adjusting force. I will discuss some brief theory, all right? We denote it by the symbol Fs, right? And its value changes from 0 to a maximum value, 0 to a maximum value. We call it the limiting value of static friction, or I will simply write it as Fs max. Okay, and remember this can adjust itself depending on how much force is being applied on the body. Okay, so for example, let's say I am pulling this towards right with a force of 20 Newton, and if friction of 30 Newton can be applied, if this value is 30, so what will be the friction that would be acting on the, let's say this body that is going to slip on the ground? How much friction is required? Only 20 Newton, right? Because I am pulling it with 20 Newton only. So if maximum value is 30, only 20 Newton is sufficient to stop the body from slipping. Okay, to stop the body from slipping. And remember, it tries to prevent the impending motion. You can remember it like that, right? Tries to prevent impending motion means the motion that is about to happen, right? The motion that is about to happen. Sometimes it may succeed, sometimes it may not succeed. And what happens if it does not succeed? What happens? Then that means that the object will start slipping on that surface. Start slipping means now static friction won't come into play. We will have another kind of friction that is called kinetic friction, right? So that comes into play when slipping is happening, right? And you can also remember this value, Fs max. It goes by mu s into normal force. I will tell you what this normal force is in a short while. Mu s is your coefficient of static friction multiplied by normal force. This is the maximum value. And what about kinetic friction? It would be mu k into n, right? Mu k into n. And remember, this comes into play when the body is slipping on the surface, right? Which means all this is not valid. Okay, don't worry, we'll cover this as well. All right, see over here. Here, I want to cover this topic, angle of repose. That is why I started with that. So let's say a body is kept on an inclined plane, right? Inclined plane like this. The gravitational force will act downwards, which you can resolve in two directions, right? mg sin theta and mg cos theta. And this you have to remember by heart. If the angle of inclination of the inclined plane is theta, the force down the inclined plane on the body will be always be mg sin theta. So you don't have to do any calculation, right? mg cos theta in this direction, and that is opposite to this normal force applied by the inclined plane on the body. So what can you say? N is equal to what? So we can say N is equal to mg cos theta, right? And this mg sin theta, what is it trying to do? It is going to pull the body down the incline. And who is going to prevent that body from moving down the incline? That is our frictional force, right? And frictional force, or I call it static friction, or I am writing here maximum value of static friction. What will it be equal to? Mu s into normal force. Normal force was how much? Mg cos theta. So this becomes mu s into mg cos theta, right? And if you remember, let's say what I'm doing, I'm increasing the angle of this incline. So what happens? Theta is increasing, right? So remember, if let's say theta I'm increasing, then what happens? This mg sin theta will increase. Now what's up with that? What's the point of this? Or what's the, let's say, benefit of this? It's pretty simple, isn't it? So let's say, for example, this is an incline and I've kept, let's say, a chalk piece on this one, right? So as I keep increasing this angle of incline, what will happen? Keep increasing this angle, this block, it will become easier and easier for the block to come down the incline. Because the mg sin theta, pulling force is becoming larger and larger, right? So that means there will come a time, or there will come a theta, right? A theta at which, let me write down, block starts slipping, right? Block starts slipping, right? And remember, if theta is very, very small, then this friction will be very, very large, isn't it? Because cos theta, if theta is very small, cos theta will be very large. And if theta is small, mg sin theta will be very low. But at the appropriate theta, the block will start slipping. So that theta we have to find. So how will we find that theta? That theta means this frictional force would be equal to this mg sin theta, right? So that means mg sin theta is equal to frictional force, that is mu s mg cos theta. Cancel mg over here. Cos theta, bring it over here. What does it become? Tan theta. So tan theta is equal to mu s. And this theta is special. This theta is special. Why? This is what we are calling it as angle of repose. Angle of repose, which means this is the maximum theta, or we can say this is the theta at which block starts slipping. Okay? Or we can write over here, this is theta r, right? At this theta, both these forces will be equal to each other, and above this theta, if it is even 1 degree above this theta, that block will easily come down, right? Because mg sin theta will be automatically more. All right, very well. So if you want me to, let's say, write a summary, right? So if let's say theta of the incline, right, it is less than angle of repose. You can remember this summary for solving your questions, right? If theta is less than angle of repose, that means the block won't be sliding, right? That means the block is at rest only. Block is at rest only, so block is not sliding. That means what will be the value of friction? The friction would be equal to this mg sin theta only. Friction won't take this maximum value. There is no need to take this maximum value. This maximum value will be taken only at angle of repose, right? So in that case, friction we can directly say it is equal to mg sin theta, right? Theta equal to theta r, we can say the block just starts slipping, right? At that theta, block is at rest, but above that theta, block will start slipping, right? So we can say block starts slipping. If you want, you can write it like that. Block starts slipping, right? And here friction, what would be the value? It is the maximum value, and we also call it as limiting value of static friction, or maximum value, and that would be equal to how much? Mu mg cos theta, or it will be equal to mg sin theta, but which theta? It is theta r, right? So if you want, you can write theta r also over here, right? And if you want, you can write mg sine theta also over here, because they are both equal, right? And what happens over there? That means block comes down, right? Block comes down easily down the incline, right? So over there, that friction, we won't say it as static friction, right? Because the block has started slipping. Here it has not started slipping, just started slipping, right? So here, please remember, this is still static friction only, okay? This is also static friction, but here kinetic friction will come into play. Kinetic friction, and what will be the value of that kinetic friction? It will be right Fk equal to mu k into n. So mu k into n. N, what was n equal to? N was equal to mg cos theta. So mu k into mg cos theta, right? Yeah, so mu k into mg cos theta, yeah, mu k into n. All right, very well. Now see here, these are pretty oral questions you can do in a jiffy, right? Coefficient of static friction is given, mu is given as √3, right? Angle of repose they are asking. What was mu equal to? Just now we did, right? Mu is equal to tan theta, right? See here, mu is equal to tan theta. So this will be equal to tan of theta. Theta is your angle of repose. Tan theta equal to √3 means theta is 60 degree. That's it. Now see this question. What is saying? Here also coefficient of static friction is √3, and in this next question also the coefficient of static friction is √3, right? That means the angle of repose is how much? Just now we did, right? 60 degree, right? But here let's say the angle of inclination, right? Let's say the angle of inclination is, let's say we can take any value, right? Let's say I am taking it as 59 degree. Then will the block start sliding? Will it? No, right? If it is less than the angle of repose, it won't start sliding. And let's say the angle of inclination is, let's say it is 61 degree. Then will it start sliding? Yes, it will, right? Yes, it will. Yes, it will. And also remember that in all these diagrams, if you want, you can also find the acceleration, right? You have to draw the proper FBD, mg sine theta, then mu mg cos theta over there. Which acceleration when I am talking about? I am talking about this case, because here acceleration is 0, right? The forces cancel each other. But in this case, you can find the acceleration, because you have forces in both directions. So net force upon mass is your acceleration. All right, very well. I guess we have come to the last question of the day, right? You're saying a monkey is descending down a vertically straight branch, right? It is descending, meaning going down. Let's say this is the monkey, it is going down with acceleration a, with constant acceleration a. And the mass of the monkey will be also be downwards, mg, right? And if the monkey is going down, the branch will try to oppose. So the branch tries to push the monkey upwards. So that force, let's say we call it by a name. Let me call that by, let's say, F only, right? And what are they saying? The braking strength of the branch is 75% of the weight of the monkey. Then minimum acceleration with which the monkey can slide down without braking, they're asking. So what's the Newton's second law you can write over here? See, mg minus F equal to ma. This is what you can write. And if you see, the braking strength is 75% of the weight. So what does that mean? Braking strength is what? This F they are talking about, right? So this F, or the maximum value of F, is 75% of the weight. So 75 by 100 of its weight, right? So you can put that value over here, put it. So what does it become? 75 by 100 into mg. You subtract them. So what does it become? 25 by 100 into mg, right? And this is equal to m into a. M cancel. 25 and 100 also cancel. It becomes 1 by 4. So what does acceleration become in the end? G by 4. right, G by 4. Now remember, we had also discussed about this breaking strength, right? Over there on the stress strain curve, I have written breaking stress. That is a maximum stress that can be applied on the material. And here it is, they are talking about the maximum force that can be applied. Okay. So I hope we are done with the session, and I hope you found this session interesting. Thank you for watching.